easier to get all your data together. Now, on your x-axis here, you're going to put in the distance. And since we're using centimeters, it'll be distance in centimeters. I know all of you may not be using centimeters. You may use decimeters or millimeters or whatever. You just be sure to use the appropriate units. Now, on the y-axis, you'll be taking the log base 10 of your value in base pairs. So since this is 1,000 kV for this band at 2 centimeters, we'll be taking the log 10 of 1,000, which equals 3. So y-axis, we have 3 over here, and 2 centimeters appear, let's say, over here, and you got set point over there. Now let's say we want to measure this band next. So, like before, well, bottom, front of bands, and you get, say, a distance of 0.5 centimeters. And that band size is 10,000 base pairs, or in other words, 10 kV. Take 10,000, log 10 gives you a value of 4, and that will be located, say, over here. You do this 5 times, and you get other points, and you add a trend line in here. In addition to trend line, we need an R-squared value. This tells you the quality of your graph. If it's below 0.9, redo the graph so you get better values. I know for a fact that these ladders are very well done. It's the reason why I chose these 2 particular graphs to put online. It's because we'll know we'll get really good R-squared values. Like they use 3 points, They use 3 points, and they still got above 0.9, so we know that the ladders are perfectly fine. In addition to the R-squared value, we also want the equation. That's critical for the next step. So you're going to get y equals some value times x plus or minus some other value. Now, you need to identify our unknown. So say that this was your unknown over here, unknown b, and what you're going to do is measure both of your bands. So if you had A, you only have 1 band to measure. If you had any other unknown, you have 2 bands to measure. You have to measure both of the bands. And I know B and C are harder to see on the graph I uploaded for you guys, so just try and do your best to find the band. If you can't, as long as you state it in your lab report that there is no band to reference, you don't have to worry about it, okay? So you can measure the top band, which is your backbone, right up there. Measure like you do. You're going to get a distance x, and you're going to plug it into your equation, and you're going to get a value of y. The same thing you can do for your second band. You're going to get another y. So we'll say y1, y2. That's only half the work, because what you did was take the log 10 of it. So to get it to the value you want, you just raise that value, so whatever this value is, 10 to that value, and now give you the size of each band in base pairs. Now, posted online should be maps of each plasmid unknown, and it should be labeled with it. I know I mentioned it at the beginning of this, but also to be certain that just look online, look at the maps, it'll tell you the sizes of each particular band that's going to be on it. Your backbone should be about 4,000 base pairs, or 4 kV, and that should line up perfectly for your Y1. Your Y2, which is going to be your insert, should be at least somewhat close to it. If it's like within like 50 base pairs, you did good. Just say that this was predicted. Slight errors in measurements may have caused the changes in it, and you're fine. If it's really off, then you're going to have to come up with an explanation. You can say overdigestion. There's a whole variety of things that could happen. And just make sure it seems logical. All right? I know it's a lot to talk about in the lab reports. I was standing up here doing it for quite a bit of time. Are there any questions, any clarifications needed, or need to go over any particular step in more detail? I know I may have left a few small things out in terms of concentration, and I know I forgot to add the voltage, but that information you should have already from when we actually did the experiments. So whatever things I missed out, just be sure to incorporate it from the actual protocol. Now, all those small things I mentioned about why we did each step is very critical. Those need to appear in your introductions. You have to be able to look at each step and understand why we're doing this. This is pretty much what your introduction is going to be looking at. All right, so that's why it's a starting point, because you have to logically explain why are we doing all this to get the plasmid out. Like, most basically, you have to at least define what each step does. What's the point of the transformation? Well, we need to make a whole bunch of bacteria. Why? Well, we need a lot of DNA. Well, how are you going to get the DNA? We're going to do a mini prep. All right. So how are you going to figure out what you answer is? Well, we're going to digest it and run a gel. You have to set that information up. But then you have to explain why each step is critical for each one. For transformation, you have to say, why do we put it on ice for 10 minutes first thing? Well, you got to say, well, the DNA needed, you have to get bacteria ready. The DNA had to sit on the surface. The heat shock opened it up so the DNA went in, and the recovery step allowed the bacteria to heal. You say something of that nature, you'll get the points for that particular section. Now, if I'm right, I believe it's 8 points for the introduction and 10 points for materials and methods. Material methods, you have to write everything you did. I mean literally everything. Concentration, amount of solution, very critical here. And a lot of people lose some points because they forget to, because I know in a lot of previous lab reports, people forget to write how much time for each plate did you irradiate for UV light. That was important. You can't say that, well, we just irradiated with UV light. Yeah, but how'd you do it? I need to know exactly how you did each and every single one of your steps. You don't have to go into detail like say, well, I used a pipette, pushed down to the thing. You don't have to say that. But I say that we had our 2 plates. We add 10 microliters of our solution to one plate, 25 to the other, and we spread it around using a sterilized hockey stick. We incubated overnight at 37 degrees Celsius, and restored them at 4 degrees afterwards. We want that sort of detail. So time, pretty much, when you write this out, make sure you hit concentration for any important chemical. Make sure time is used. And volume. Make sure you hit these 3 points for most of the chemicals. Centrifugation, you can mention number 1, so just be sure to say at least at some point that we use 10,000 RPMs through the duration of the experiment. You can cut corners as long as you qualify it, as long as you state that we did this in some sort of way. All right? Let's see what else I need to say about this.
I have a question. What did you do differently on the new gel that because our original gel didn't work?
Well, we haven't fully figured out why your gels weren't working. We think there was a problem with one of the chemicals. We don't know if it was the agarose or the TAE. There was issues, so I ran the gel on Thursday. I just used my personal stock from my lab just to make, because I know that stuff works.
Yeah, the others told us that agarose could have been contaminated.
It could have been the agarose, maybe contaminated, or there was something wrong with the concentration in TAE. Those are the 2 biggest possibilities. So if you want to mention any lab report, go right ahead. But I think Brahma, we won't even talk about the other gels. Put 1 sentence saying that our gels didn't work,
Yeah, because they
and
didn't
you can pass the other off as your own.
there could have been anything wrong that day.
Yeah, we don't have an answer for that one.
Yeah, just say that our gels didn't work. That's it. I'll be fine with that. Because gels don't work. Most
Are there any other questions? Because at this point, I think we'll just take a look at your lab reports more specifically and we'll give a quick proofread and see where everything's at.